All right, I hope this works. I've been having nothing but trouble with this setup. I don't know why. It used to be very reliable. But anyway, okay. So what I'm going to try to do here is go over another approach for solving statically indeterminate structures. This is what we call the so-called force method. And this is in section 4.5 in Hibbeler. Some people find this a little easier to use. Like you don't end up having an approach where you have two equations for two unknowns and you carry two variables that you solve for simultaneously. But it's a little bit of a different thought process, so I will put it out there. It's okay to do either approach if you want. It's up to you what you feel more comfortable with. So let's start with the example that we did in class using the straightforward approach, okay? So we're going to consider a stepped beam that's constrained on both ends. All right, so it's a point A, B, and C, and I gave a 10 kilonewton force at point B to the right. All right, and this is made out of steel, so we have E equal to 200 gigapascals. The length from A to B is 1 meter, and from B to C is 1.5 meters, okay? This section AB has an area of 20 square millimeters, and this section here from B to C has an area of 10 square millimeters, okay? So as we talked about in class, this is statically indeterminate, but instead of using the two equations, one coming about from sum of forces in the x direction, as well as the compatibility condition that the total elongation is 0, we're actually going to use sort of a trick with superposition. All right? So remember superposition, when we have a linear system, we can actually consider the superposition of forces separately, and then the actual solution is the sum of those. Because everything's linear, you can just add them together. All right, so we're going to actually break this up. Well, first thing we're going to do is we're going to eliminate one of the constraints. So let's eliminate the one on the right. And I'll kind of explain what we're doing here. So now we're going to replace this with a problem that looks like this. We have our 10 kilonewton force here. And here we go. We've eliminated that constraint. And so now I'm going to kind of ask the question, what is the force that we would need on the right-hand side such that the whole structure does not elongate? Basically so that it still sits in these constraints. Okay? All right. Now, the way we're going to do that is actually not this way, because this would just basically get us back to the same approach we had before. But we're going to solve this with superposition, okay? So this problem is going to be replaced by the following two problems. I'm going to denote the first one with a Roman numeral 1. And so this is everything but that unknown force on the right. So if I had other known loadings, they would all be in here anyway. All right. And now we're going to superimpose on that a second loading condition, which is just simply this unknown force on the right. Everything else is the same. We don't have the 2 kilonewton force. And here I'm going to put a force on the right. Okay, now we really don't know what this is that maintains the length of the entire section, that prevents it from elongating. But since we're going to consider the superposition of these two, I can isolate the effects of this. So I'm going to just give this a unit value. I'm going to give it a value of 1 kilonewton. You can pick whatever you want, but you'll see why 1 is a nice number because we'll just scale it. So now the idea is, here's how this is going to work, right? So we're going to consider the superposition of these two load conditions. So from this one, I am going to get an elongation from A to C due to that loading condition, all right? So it's going to stretch, okay? Now, the question is, what's the force we have to do on point C to push it back to 0? So from this, I'm going to get another elongation from A to C, but this is due to the second loading condition. Now, unless I get really lucky, this will not be the right value. But let's say this moves 10 millimeters out, and then this moves 5 millimeters back in. Well, you know that actually to get this to move 10 millimeters back in, we just need to double this. So, that's why we picked the unity value of that, okay? All right, so let's do it. So again, that's the concept, okay? So we remove one of the constraints, and that introduces an additional force, the one that's going to constrain it and push it back to be no elongation. All right, but we don't know what that is. So now we're going to break it up into two loading situations by the use of superposition, or at least that justification. So the first one has everything except that unknown force. So in this case, we only have one force, but if there were multiple, you would have it. And then from that, we figure out the elongation, as if there was no force here. Then we figure out the problem with just the force, how much that would push it back, basically correct this. And then we scale it so that this would equal the negative of this. So basically enough so it pushes it back. And that's going to give us, then we superimpose the two together, and that'll give us the total solution, okay? All right, so let's do it. All right, let me start on another piece of paper, okay? It's probably easier. Let's still keep this up here. Okay, so let's first do this problem. So this one's pretty simple, right? So if we look at case 1, we're going to be something that looks like this. This is a pretty simple problem because I have the 10 kilonewtons acting this way, and that means I have a reaction force on this side of 10 kilonewtons, okay? Pretty simple problem. The only elongation is going to be the elongation between section AB. There is no elongation between BC because there's no loading in here. So actually the elongation from A to C is going to equal, this is for the first load case, is going to equal the elongation from A to B, because this elongation from B to C of the first load case, that actually goes to 0 because there's no force there. Okay, so it's just this. And now that is going to be the internal force, which is the 10 kilonewtons. All right. The length of this section, AB, which is 1,000 millimeters. The cross-sectional area is 20 millimeters squared, and Young's modulus is 200 gigapascals. Okay? And so now this is going to give me the elongation if that right end support was removed and there was no force acting there. And so when you do this, this will come out to be 2.5 millimeters. All right? So that means in this situation, just under this loading, this will stretch out 2.5 millimeters. Okay? Okay, so it's going to basically go So now we want to find the force in the second load case that'll push this back 2.5 millimeters. So I'm actually going to do it for 1 kilonewton. And like I said, if it's too much, I'll scale it back, or if it's not enough, I'll scale it up, okay, to find the actual value. So again, you can see the reason why people like this approach, and it's not a unreasonable advantage, that we don't have to solve for like systems of unknowns, right? We kind of just do straight ahead calculations and then we scale it at the end. So let's now consider the elongation for the second case. All right, so now it looks like the following. I put a 1 kilonewton force on the right-hand side, and so that means on the left-hand side, the supporting reaction is going to be 1 kilonewton. This is going to be point A, B, and C. And so this is the second load case. So the elongation here for the second case is going to be the elongation from A to B plus the elongation from B to C. And now in this case, both sections have a compressive force of 1 kilonewton, right? So if we cut it here, we have a compressive force of 1 kilonewton, and if we cut it here, we also have a compressive force of 1 kilonewton, okay? But different lengths in cross-sectional areas. So here we go. So now if we do this, let's first do it for AB. So we have, and they're both negative, so I'll put the negative out here, but that's fine, right? Well, just do it this way. So we're going to have negative 1 kilonewton, right? Length of 1,000 millimeters. Cross-sectional area of 20 millimeters squared. 200 gigapascals is Young's modulus. Okay, that's the elongation in the second load case from point A to point B. And then for BC, its internal force is also 1 kilonewton in compression, so I put the negative there. Its length is 1,500 millimeters, and over its cross-sectional area, which is 10 square millimeters, and 2 looks like a G, I'm sorry, 200 gigapascals is Young's modulus. So this is the elongation from the second load case from points B to C. All right, and so when you do this, you will actually put in all these numbers, you can calculate it, you're going to find out that this elongation is minus 1 millimeter, okay? All right, so it only pushed it back 1 millimeter. We needed to push it back 2.5 millimeters, all right? So that means that this force needed to be 2.5 times greater than this. So actually this force should be 2.5 kilonewtons. Does that make sense? So if we had this as the loading condition, where we put on this end 2.5 kilonewtons, and then we'll put a reaction force back here of 2.5 kilonewtons, we know from linearity that this would give us a elongation from A to C equal to minus 2.5 millimeters, right? It has to be 2.5 times this loading, okay? So this is actually going to be the reaction force that prevents the whole thing from elongating. So what does that mean? Okay, so let's go back and look at what we have. So this original problem with the unknown reaction forces at both ends now is going to become the superposition of these two problems. Our first one where we have the 10 kilonewton force this way and then the 10 kilonewton force this way. Okay, this was case 1. All right? So this ended up elongating this section by the 2.5 millimeters. All right? Now we know if we also consider the second load case, like this, and we put on here a compressive force of 2.5 kilonewtons. And that means that we'll have the reaction force in this case at 2.5 kilonewtons. That this will have the effect of compressing this back 2.5 millimeters. So when you superimpose these two, the net elongation is 0. So it fits in those fixed walls. So that means the actual, we're going to add those together, that in actual is as follows. All right, so we just add up everything we got from the two load cases. All right, so we have 10 newtons acting this way, 10 kilonewtons acting this way, and then 2.5 acting this way. So when we add these together, the net force is 7.5 kilonewtons acting to the left. All right, now here, all we have is just the 10 kilonewtons. There's no additional force here. So we have the 10 kilonewtons this way, which, right, that's our external force that's given. And then we have the 2.5 kilonewtons acting at the right-hand side. Okay, so now that's the actual, these are the two reaction forces, A, B, C. So this is actually the force at A, and this is the reaction force at C. All right, and now you know what those reaction forces are, so you can go back and figure out the stresses, right? So the stress would be, in AB would be the 7.5 kilonewtons over the cross-sectional area, right? So the stress in section AB would equal that 7.5 kilonewtons over the 20 millimeters squared, right? Which is, 2.5 divided by 7.5. Third minus 6, 3, so kilopascals. So it's going to be 0.75 kilopascals. Is that right? I think that's right. And then likewise, you can get the stress in BC. That's going to be the 2.5. It's in compression over its cross-sectional area, which is 10 millimeters squared. And that is going to be minus 0.25 kilopascals. Right? Okay. So that's the approach. Okay, so let's just review. So the logic. Okay, so, right, normally we start off with this problem, and as we did in class before, we just directly drew the free body diagram as follows. Where we would have put a force here at C and a force here at A, right? And then we would have solved the force balance equation and the total compatibility equation together. And we would have carried these unknowns FC and FA through the calculations. Instead of doing that, we've used this logical argument that we're removing this constraint, and that'll stretch the structure, but then we want to figure out the force that'll then bring it back so the total elongation is 0 and it would fit back in the rigid supports. Not knowing what this force is, we set it equal to 1, and then we can scale it so that it equals the negative of this. And that's all we did here, right? So we exactly, not here, in here, right? We went back, figured out for the first load case, where the unknown force is removed, we got an elongation of 2.5 millimeters. Then we apply a unit force, 1 kilonewton, to the left. See how much that compresses it. It turned out it only compresses at 1 millimeter. We needed actually 2.5 millimeters. So that means the force needs to be 2.5 times greater than this. So that gives us 2.5 kilonewtons. Then we superimpose those together. All right. And this case and that gives us the final case here. All right. So again, like I said, the logic of doing it is maybe a bit more involved, but once you understand that, it's really the same for everything. And like I said, the advantage of this one is nice in that it doesn't have, you don't have to carry the variables, right? So you can basically just go through and forward compute everything, which I know for some students is something that they like. Okay? All right. Hope that's helpful.